Ladies and gentlemen, in this lesson, I will be proving to you the proposition that we've seen in lesson 5, symmetric groups. This proposition says that any permutation that shuffles a finite number of elements is in fact a product of disjoint cycles. So let us see this proposition formally. The proposition says that if E is a non-empty set, in other words, there is at least one element, and sigma in SE is a permutation that shuffles a finite number of elements. In other words, the set in which sigma x is not equal to x is a finite set. Then the proposition tells us that sigma is in fact a composition of pairwise disjoint cycles. Pairwise, it means each two cycles together in the composition are disjoint. Let us move on to the proof of this proposition. The way in which we're going to prove this proposition is a certain technique called induction. Induction is a technique that we use to prove a certain property holds for all natural numbers. Natural numbers being the numbers 0, 1, 2, 3, 4, and so on. Well, technically, those will be whole numbers, but it doesn't really matter if we start from 0 or 1. The point is, we're going to prove this certain property holds true for all n bigger than 0 or bigger than 1. In this case, we will start by 0. But what is n here? Well, if we want to prove a property on a set of permutations, then we need to put n to be the cardinality of the set, and we need to increase the cardinality n as we go on. So the induction process works like this. First, we prove the property holds true for the base case n is equal to 0. And then afterwards, we assume that the property is true for the case n is n minus 1. And using that assumption, we prove that the property holds true for n. That way, we can have a certain domino effect when it comes to proving for all n bigger than or equal to 0. So let us start with the base case of this proof. In induction, the base case would be the case of n is equal to 0. But before we begin the base case, we need to figure out what n would be in this case. So n would be the cardinality of the set of permutations. So the induction would be on the cardinality of f sigma. Not quite the set of permutations, but the set f sigma, which is defined to be the set of all the x in E, all the elements in our set, such that sigma of x is not equal to x. In other words, f sigma is the set of permutations, it is the set of elements that are not fixed by sigma. If this set is empty, in other words, if n is equal to 0, so if n is equal to 0, then the set is going to be empty. But that means that there are no x that sigma sends to a different x. In other words, all the x are fixed. So sigma x is equal to x for all x in E. But if sigma x is equal to x for all x in E, that means sigma has to be the identity permutation. That means that sigma is the identity permutation. And the identity permutation, written explicitly, it can be written as, let us say, E was the set that contained Z1, Z2, Z3, these elements, etc. So then the identity permutation on the set E would look a little something like this in terms of cycles. So we would say it is the cycle Z1, so just a one cycle, followed by the one cycle Z2, followed by the one cycle Z3, and so on. So the identity permutation is a product of pairwise disjoint cycles. These cycles are all pairwise disjoint, thereby proving our base case for the proposition. In the induction hypothesis, it is customary to assume that the hypothesis holds true for all sets with properties of cardinality less than n. So this is what we're going to write here. We suppose that the result of the proposition is true for all tau in SE such that the cardinality of f tau being the x such that tau of x is not equal to x, is less than n. The first order of business is to let x be an element in f sigma. If x is an element in f sigma, then by the definition of f sigma, sigma of x is not equal to x. Now, let us prove that sigma of x is also in f sigma. So not only is x is in f sigma, but sigma of x is in f sigma. Proof by contradiction. We will assume the opposite. Assume that sigma of x is not inside f sigma. If sigma of x is not inside f sigma, then that means if we apply sigma to sigma of x, we should get back the same element sigma of x. This is because sigma will fix sigma of x. So if we have this relation, all what we need to do is apply sigma inverse on both sides to arrive at our contradiction. So we will apply sigma inverse on the left and right hand side. So sigma inverse, sigma of x is equal to sigma inverse, sigma of x. And we will use the fact that the inverse multiplied by the element is the identity. So identity, sigma of x is equal to identity of x. And the identity has no effect on any element. So this is just sigma of x is equal to x. But we have just said that x is an element in f sigma. That means that sigma of x is not equal to x, which is a clear contradiction with what we've just arrived at. And this stemmed from the fact that we assume that sigma of x is not an element in f sigma. So this is a contradiction, and this is the symbol that we use. So this means that sigma of x has to be an element of f sigma. Now we've just proved that if x is in f sigma, then sigma of x is in f sigma. But what we can notice here is that we can repeat this process to say that sigma squared of x is also in f sigma, and sigma cubed of x is also in f sigma, and so on, by using the same argument. So we have the elements x, sigma of x, sigma squared of x, sigma to the third power of x, and so on are all elements in f sigma. Now, since f sigma is a finite set, we can't expect to arrive like at an infinitely many number of elements, right? We need to, at a certain point, go over some element we've already crossed. So there exists an n2, a natural number n2, and a natural number n1, which is less than n2, both bigger than or equal to 0, such that sigma to the power n2 x is equal to sigma to the power n1 of x. So at a certain point, we will find that we have gone over two different n's, but the same result, because f sigma is a finite set. So what we can do here is we can use the same sort of argument to say I can multiply both sides of the equation by sigma to the power minus n1 to obtain the following. And now I just simplify. I obtain this becomes by exponent laws sigma n2 minus n1x is equal to sigma n1 minus n1x, and this gives me sigma n2 minus n1x is equal to sigma of 0x, but by definition of to the power 0, we have that this is just the identity. So identity x is just x. So we have this relation because f sigma is a finite set. So we let m be this n2 minus n1 that we've just found. We have, by substituting m in the equation, sigma m of x is equal to x. So there is such an m such that sigma to the mx is equal to x. Since m is a non-negative number, we can choose m to be minimal. In other words, m is the smallest non-negative number such that sigma m, sigma to the m of x is equal to x. So any other number less than m, we have to have that the sigma to that power of x is not equal to x. So this is what we're going to be basing our argument on. So now, because of this minimal choice of m, we can immediately apply this fact by saying that if we have x, sigma of x, sigma squared of x, all the way to sigma to the power m minus 1 of x, all these elements are distinct and they're in f sigma. Because remember, m was chosen to be the smallest non-negative power of sigma, such that sigma of x is equal to x. So any power smaller than m would have to have sigma of x not equal to x, thereby being in the set f sigma. So of course m here will be less than or equal to n, which is the cardinality of f sigma. Now, using this, we will construct a cycle. Since all these elements are distinct, we can put them in a cycle that we will call mu. So let mu be a cycle composed of these elements. So mu is a cycle that takes x and sends it to sigma x. It takes sigma x and sends it to sigma squared x. Sigma squared x is sent to sigma cube x. And every sigma to the power n x sends it to another power n plus 1 x, all the way until the sigma to the m minus 1 x, and sigma to the m minus 1 x sends to sigma mx, but sigma mx, we have said that it is equal to x because of the definition of m. So we can close our cycle and repeat our process like that. So mu is chosen to be this cycle, but just notice by the way that this cycle is exactly the application of sigma repeatedly on x. So here x, when you apply sigma, you get sigma of x, and when you apply sigma again, you get sigma squared of x. So mu is expected to be nothing but a cycle that revolves around x that is contained inside the application of sigma. So now this special construction of mu, which is very useful in this case, would give us a natural construction of another permutation we call tau, and tau we define it to be sigma composed with mu inverse. So mu inverse is the permutation that goes the opposite direction from mu. Mu inverse would take sigma x and gives you back x, for example. So we need to see what does tau do on the elements x, sigma squared of x, etc. So tau of x, by definition of tau, is equal to sigma composed with mu inverse x. So what is mu inverse x? Well, remember, I just said that it takes it in the opposite direction from mu. Where mu would have taken it to the right, mu inverse would take it all the way back to the left, or to the end of the line. So it gives us sigma to the m-1 of x. So this is equal to sigma composed with sigma m-1 x. And now we can use exponent rules to say this is equal to sigma to the 1 plus m-1 of x, and that's equal to sigma to the m of x. But sigma to the m of x, we already know that this is equal to just x. So now, in conclusion, tau sends x back to x. So tau fixes x. Okay, let us see what tau does to sigma of x. Tau of sigma of x. Well, tau of sigma of x, in a similar fashion, we will use the definition of tau first. And this is equal to sigma of, so mu, if mu takes sigma of x to sigma squared of x, then mu inverse should take it the opposite direction, which is just x. So it will be sigma of just x. Sigma of x is sigma of x. We keep it like that. So tau carries sigma of x to sigma of x. And if you repeat the process with all the elements, you will find that tau sigma to any power k that is non-negative x is equal to itself. Very interesting stuff. So tau fixes all of the elements that are from x, sigma squared x, all the way to sigma to the m-1 x in particular. So letting k be equal to m-1, we see that x, sigma squared x, all the way to sigma to the m-1 x are in, oh, they are not in f tau. And what is f tau? Remember, f tau is all the y in E such that tau y, because we're dealing with the permutation tau now, not sigma. So all the y in E such that tau E is not equal to E. Tau y is not equal to y. So now we have that all of these elements are fixed by tau from the previous argument, and therefore they are not in the set f tau. Okay, they are not in the set f tau, so x, sigma squared x, all the way to sigma to the m-1 x do not appear in the cycle tau. Because remember, if you have a cycle, let's say 1, 3, 4, 6, then all of the elements here, they are not fixed by the permutation, because 1 is being sent somewhere else, 3 is being sent somewhere else. So any element that is not in the list is fixed by this cycle. Let's say 5. So 5 here, because it's not in the cycle, it is fixed. And the same goes with these elements. So because these elements are not, they are fixed by tau, then they do not appear in the cycle of tau. So because they don't appear in the cycle of tau, but they do appear in the cycle of mu, by the definition of mu, that means tau and mu contain no elements in common. So tau and mu are disjoint cycles. We're almost done now. So now that we have proved tau and mu are disjoint cycles, it suffices to prove that tau is a composition of pairwise disjoint cycles. To do that, we want to use the induction hypothesis, and to use the induction hypothesis, we want to prove that the cardinality of f tau is less than n. F tau is defined to be the x such that tau of x is not equal to x. So we want to prove that this cardinality is less than n. But this n is just the cardinality of f sigma. So essentially speaking, we want to prove the proper containment of f tau in f sigma. So if we want to prove a proper containment of two sets like that, we will make it a bit easier first. Let f tau bar be the set that is exactly opposite to f tau. So f tau bar be the set of x such that tau of x is equal to x. And f bar sigma, of course, is defined similarly. So x such that sigma of x is equal to x. So we want to prove now, essentially, this, but this is equivalent to proving f sigma bar is contained properly in f tau bar. Just because of the nature of how the definitions are opposite to each other, we have the reverse inclusion in this case. So we want to prove this, which will prove the other one. So prove f bar sigma is properly contained in f bar tau. To prove that a set is properly contained in another set, we need to prove two things. First, prove that f bar sigma is contained in f bar tau. And the second is to prove that f bar sigma is not equal to f bar tau, which will make it a proper containment. So the set f bar tau would be strictly bigger than the set f bar sigma. So to do the first step, we usually assume there is an element in f bar sigma, and we want to prove that this element, arbitrarily chosen, would be found in f bar tau. So let y be in f bar sigma. If y is in f bar sigma, by the definition of f bar sigma, we have that sigma of y is equal to y. If sigma of y is equal to y, we've seen earlier that the elements x, sigma square x, all the way to sigma to the m-1 power of x are not fixed by sigma, just because of the nature of m. So y cannot be any of the elements that we've mentioned beforehand. X, sigma x, all the way to sigma to the m-1 power of x. If y is none of these elements, recall that the definition of mu as a cycle containing x, sigma x, all the way to sigma to the m- power of x, this definition of mu says that, essentially speaking, since y is none of these elements, so y is not contained, y does not appear in the cycle mu. So if an element does not appear in the cycle, that means the cycle does nothing to that element. It fixes it. It does not send it anywhere else. So mu of y is equal to y. And remember, what we're trying to prove is that if y is in f bar sigma, then y is in f bar tau. So at the end of the day, we need to use tau. So tau of y, by definition of tau, if you remember, it's sigma of mu inverse of y. Now what is mu inverse of y? We can apply mu inverse, we can compose it at both sides of the equation to have mu inverse mu of y is equal to mu inverse of y, and mu inverse and mu is just the identity, which is just y. So this gives us y is equal to mu inverse of y. So this is just going to be y, and this is just equal to sigma of y. And sigma of y is already known to be equal to y. So this means tau of y is equal to y. Tau fixes y, so y is an element. So y is an element of f bar tau. So if y is an element of f bar tau, and this is for any arbitrarily chosen y in f bar sigma, that means that we have just successfully proved the inclusion f bar sigma in f bar tau. It is time for us now to prove that they are not equal as sets. But remember, since sigma is not the identity, we assume that after having proved the base case, we assume sigma is not the identity, and x is not equal to sigma x, because we have already defined x to be an element in f sigma. We have this fact that x is not equal to sigma x, but tau of x, we've already said it is equal to x. So essentially speaking, we have found an element such that tau of that element fix itself, but sigma of that element is not fixing itself. So essentially, we have found an element that is in f bar tau, but not in f bar sigma. So we proved that f bar sigma is not equal to f bar tau, and that element is x that we've used. So combining this fact and this fact together, we say that f bar sigma is properly contained in f bar tau, which means that f tau is properly contained in f sigma, which means that if we take the cardinality of both sets, the cardinality of the first set is strictly less than the cardinality of the second set, which is taken to be equal to n. So the cardinality of f tau is strictly less than n, and we can finally use the induction hypothesis. So using the induction hypothesis, we have that tau is a composition of pairwise disjoint cycles. But since tau is equal to sigma mu inverse, all that we need to do is apply mu on both sides. So we compose mu and we get tau mu is equal to sigma, and we've already seen that tau and mu are disjoint cycles, and now we've seen that tau itself is a composition of the disjoint cycles. That means that sigma is a composition of disjoint cycles, thus completing the proof of this proposition.